So far I have discussed about the performance calculation for non-tensor cores, just like FP32, FP64 and INT32 cores that are available. And now I will discuss about how you can calculate the FLOPS calculation for tensor cores. Here you can see that the two tables is present. First one is this and second is table is this. Both table I have taken from the NVIDIA website, and it will help to calculate, because in a specification sheet if you see the table 2, so here specification sheet is mentioned here 125 petaflop. Thing is that how I can calculate this flop by the simple mathematics applying on the compute cores that are available. So, first thing we must know that tensor cores basically handles 4 matrix multiplication in one clock cycle. So, when I am talking about the 4 matrix multiplication, it involves a multiplication of 2 4 by 4 matrix, and which results in another 4 by 4 matrix. That means, in a single dot product requires 4 multiplication and 3 addition operations to be performed. So, we can say that one element computation of 4 by 4 matrix requires 4 floating point operations per second, because resulting matrix has 16 elements. 4 by 4 matrix, it has 16 elements. So, how many flops? Because we know that per element it is going to be 4 flops per second. So, for 16 element it is going to be 64 flops per second. So, now let us do some computation. We apply the mathematics, simple. So, how you can do the calculation in calculating the theoretical floating point performance. So, first of all you have to count the number of tensor cores multiplied by the flops for matrix multiplication, because we know that tensor core can handle only 4 by 4 matrix multiplication in one clock cycle. Next parameter is the frequency. Obviously, we cannot ignore it, because every device works on the frequency, and if I am talking about FMA, so it is always compute 2 operations per cycle. So, as per the previous table you can see here, as per the previous table you can see that how many tensor cores are available in GV100 card, that is 640 cores. So, you can count this value 640 cores, it should be multiplied by 64 because of the flops for the matrix 4 by 4, and the frequency we know that it is supporting 1.5 gigahertz and FMA is 2. So, it is nearly giving me around 125 teraflop. Next we move to the another card, that is a A100 card. Table is same, but specification I have taken for A100 is mentioned here. Here you can see that there are some changes, some modification has been done by the NVIDIA in this architecture. So, now it supports FP64 9.17 teraflops, but as well as you can mention this one where I mentioned the question mark, that this is telling that FP64 tensor core operation is also possible, but earlier in V100 this was not possible. So, such kind of changes is always occurs. So, that is recommended, always refer the specification sheets to know the changes or new changes has been done by the manufacturer in that particular GPU or new architecture. So, let us do the calculation for this. As usual, the tensor cores can handle only 4 by 4 matrix multiplication in one clock cycle for FP64 element. And another feature they have added here, extended to 8 into 8 matrix multiplication for FP32 and there is no FP32, there is a tensor FLOP 32, it also supports the FP32 as well. So, this is a big change. First change is it supports 4 by 4 matrix multiplication, that is for FP34 FP64, and if you are working on TF32 or FP32 data types, it can be extended to 8 into 8 matrix multiplication. So, if you are thinking for FP64 computation, so one element of the matrix multiplication requires 4 flops. So, resulting is 64 flops per second is possible. Next, you can see a tensor core, it is for A100 card, you can see this line, you just focus on this architecture Ampere A100. So, FP64, so you can see that this number is 64 and how many SMs are present. So, SMs are present is 108. If you want to see where this value is mentioned, so you can see that this value, total number of SMs, and 2 is for FMA, and NVIDIA A100 works on 1.41 gigahertz frequency. So, if you multiply these 4 components, then you will get the value of 19.5 teraflop, which exactly match this value. So, this is a way you can calculate the tensor core performance mathematically, as well as you can verify these values with the specification sheet. Now, I will do the calculation for tensor core FP32. Formula is always same. So, you have to find out how many tensor core per SMs are present. You can see here 512 tensor cores are present per SM. This is the value. This is multiplied by 108 and remaining parameters are always same, and you are getting this value 156 teraflop. You can see that if you match this value from here, you will see this value. So, means you have learned about how you can calculate the theoretical peak performance of computing device, especially the NVIDIA GPU mathematically, and how you can verify with the data sheet. Now, I will discuss about the memory bandwidth, how you can do the calculation of memory bandwidth of underlying GPUs. Before that, you must know about what are the types of memory that is supported by GPU. So, there are 2 types of GPUs memory. First one is GDDR, graphic double data rate, and second one is HBM, high bandwidth memory. GDDR, yes, I think you can relate with DDR that was used in host system. So, they are almost same, but GDDR is specially designed for use in graphic card and optimized for use in graphic cards. It is faster than DDR memory, which are used in a host system, and transfer more data at once at higher bandwidth. HBM is designed to provide large memory bus width. It is slower than a single GDR chip, but wider bus, smaller capacity and stackability and scalability makes it more powerful and efficient and faster than GDR memory. So, here you can see the comparison table in terms of various parameters. In terms of memory bandwidth, so you can see the GDDR has lower memory bandwidth than HBM. Memory channels, GDDR has multiple and many channels to transfer the memory, but HBM has only few memory channels. In terms of memory interface, wider data interface 32 or 64 bit, narrower interface with stack vertically. So, there is 128 bit per stack. If you see the capacity per stack, so in terms of that it is lower and HBM has a higher. Latency for GDR is slightly higher, but HBM always provide low latency due to the proximity to the GPU. In terms of power efficiency, GDR is less efficient, HBM is more efficient. In terms of form factor, it is spread across the PCB, but it is stacked vertically, compact form factor, it is always inside GPU. In terms of cost, it is a less expensive and HBM is more expensive due to the 3D stacking and packaging. So, let us see the internal view of GX 1600 card. So, where the GDDR is placed. So, you can see these chips. This is a GDDR chips that can be placed surrounding this is GPU. So, that means the memory on the GPU depends on two parameters, means number of chips that is surrounded. Just look at here, two spaces are not being used. If we add one more chip, the capacity of the GPU card will increase. And another parameter is that instead of many chips, I can use one chip with more capability, more data capacity. Suppose this chip is of 1 gigabyte, instead of that I can use 4 GB chip. So, then that is another way GPU's memory can be increased. Let us do the calculation of memory bandwidth. So, what are the parameters actually required here? First one is a total interface width is required. So, it depends on, because each chip has a fixed number of data bus. So, that is the interface width. It should be multiplied by the number of chips on the card. Suppose this has a 16 bit bus interface, but in total if you multiply it by number of chips are 6, so you will get the total bus width. Then let us calculate the theoretical memory bandwidth. So, first is memory interface width, what you are calculating from here, it should be divided by 8, 8 is the number of bits, it should be multiplied with the base clock speed. Clock speed, because if you see look at the data sheet, so they always mention the clock speed for that particular memory. So, you have to use that clock speed from the data sheet. Then it is a data rate, that is also present in the data sheet, you can get it from there. Apart from this is a fixed parameters, apart from that there are some data pumping technique are being used in a newer version of GDDR, and apart from that there is a PAM signaling techniques is also used. So, in PAM4 is a signaling schema, so that it will tells that how many bits you are going to transfer at a time. So, that is the reason whenever you are calculating, you have to take care of that whether pumping technique has been used in particular GPU or particular memory that is mentioned, or it is whether it is supporting the PAM4 signaling or not. So, that two features we have to take care of, because it is not available in all GDDR memory. So, that is the reason I am just mentioned here, ignore the data pumping technique and PAM4 signaling if DDR memory does not support them. It is always recommended to refer the data sheets or specifications for base clock speed, data transfer rate and data pumping technique. Find data width of each chip from data sheet and number of such chip on the card. from data sheet if you are interested to know more. Otherwise, they simply mention that in the data sheet this is a memory bandwidth and this is the total capacity of the memory is present on this card. But if you want to do how it has been calculated, only this mathematical formula you have to apply. Quad pumping is a pumping technique which is used in GDDR5. So, quad pumping basically increases the effective data transfer by using the multiple data channels or increasing the data transfer per clock cycle, while PM4 increases the amount of information transferred per signaling instance by using the different amplitude level. So, simple meaning is that when you are using PAM4, so it will transfer 2-bit information rather than 1. So, because of that number of bit has been increased, so amount of information transferred is also getting increased. And another side, the quad pumping technique basically telling you that how many of transfers are happening. Suppose there are PAM4 and this data is transferring 4 times per cycle. So, almost 8 bit you are transferring in one cycle. So, this kind of logic you have to apply here. So, here is one table and one I have calculated for you and remaining is left for further practice for the learners. So, look at this card GTX 1660 and this card they uses the GDDR5 memory. If you see the data sheet, if you see that there is a 32 bus interface width per chip is 32 and there are number of chips are 6 and it supports the double data rate. So, then it is called 2 DDR. So, number is 2 for DDR. Operation per cycle, pumping technique it use. So, it use a pumping technique. So, pumping technique is because it is using quad pumping technique. So, we have to apply the value 2 here. When you multiply the signaling schema it is using, so you can say that it is using NZR. It should be not NZR, it should be NRZ, non return to 0. And base clock frequency is given you 2001 approximately 2 megahertz. So, when you apply that formula on this, you will get the 192 gigabyte per second. The formula is that, so how many bits are there? So, it is around 32 multiplied by 6, it should be divided by 8, 8 is a number of bits and then it should be multiplied by 2, 2 is for DDR because of double data rate. Operation per cycle, pumping technique is it is not, if you are using then also 2 and then base clock frequency is also 2. So, if you do that, if you calculate this value, so you can cut this thing and whatever the value is coming around, that is comes around 192 gigabyte per second, you can do the calculation. But look at here, data rate I have used only 2 DDR here, but when I am using other card RTX 2080 and RTX 3080, so there is a PAM4 signaling is also has been used here. So, in this scenario you have to check, it has used QDR, it has used QDR, because of the PAM it transferred 2 bits. So, again you have to go back to the formula, you have to apply these two, data pumping technique as well as signaling technique. So, because in signaling technique it is mentioned it is a 2 bit, so you have to multiply with the results 2 bits, so you will get your answers here. So, you can do yourself by applying the formula I discussed. Now, I am discuss about the high bandwidth memory HBM calculation. So, I have 2 images are there in front of you. So, you can see that the HBM is present on the GPU, you can say it is a stackable, it is showing the stacking of the HBM memory. So, it is a it provides high proximity because it is very close to the GPU. So, let us do the calculation for I have taken here for NVIDIA V Tesla Tesla V100. So, memory interface width as per the data sheet it is mentioned 4096 bit HBM2. So, what is the theoretical bandwidth? So, you have to width you have to multiply it by the bit here and the frequency that is mentioned, and should be multiplied by data rate for DDR2. So, then you can calculate its value is 900 gigabyte per second it can transfer. Similarly, you can refer the data sheet for A100 and you can check what is the maximum theoretical bandwidth is mentioned in their data sheet and apply this formula, gather this information about bus interface width, that is 5120 bits. It is also using HBM2 or 2.5, I am not sure. So, then you can calculate 5120, it should be divided by 8 because I am going to calculate in gigabyte. So, that is why I have to divide it by 8, and then frequency is mentioned and double data rate, 2 is for double data rate. If you multiply, you will get the answer 1555 gigabyte per second.